Okay, picking up from the last video, recall that we had calculated this area here, and the 0.3461 corresponds to this area, and same thing here. So we would need to add these together in order to get the total probability. And if you do that, you'll get 0.692. Okay? 0.692 would be this entire area here. Okay. All right, now you can do this with the tables like we did, or you can use Excel. So let's go into Excel here and pull this up here. And what we're going to be using is the function called normal.distribution. We've used this before. We're going to put our x value in here. Well, we want to find out first this 0.65 as our x value. So we'll put 0.65. We know the mean is 0.6. And the standard deviation we calculated as 0.049. And then we want cumulative. Okay? And it gives you the value here. Now again, that tells you from the left tail all the way to here. Okay, so that's 0.8462, 846. That's right, and that's, we chopped off this 50% from our table, getting 0.346. And then if we want to find the value up to this point, we would just plug in an x value of 0.55, and you see it's 0.1537. So we can take those two values, let me go back here, 0.65, and populate this. So that is the probability of getting a value in this range. And then let's use the same formula, but populate it for 0.55. And that means a probability of getting a value to here. And then we can subtract. And we get 0.692, which is what we got in our computation here, right? We doubled these. So, there's multiple routes to getting these answers, but Excel is definitely a pretty user-friendly one. Then let's take a look at the last question. It says, what is a probability of getting a sample proportion below 10%? Well, you can use Excel again, and same function, norm.dist, and then the x value now is going to be 0.10, right? The mean is still 0.60. The standard deviation is 0.049, same as before, and cumulative. And you'll see that it's 9.50556 e to the negative 25, which means it's essentially 0. But that tells us down here, what's in this tail, right? Because we're starting with the left tail and going to this point here, 10%, which means we have almost no probability of that occurring. All right, let's wrap up this question by just reminding ourselves why we didn't use the finite population correction factor. The reason is, it says we drew 100 people in our sample from a population of working professionals that have a college degree. Well, that's a big group. So we can assume that the 100 is much less than 5% of the population. So that's why when we calculated this standard error, we didn't use the finite population correction factor. Okay, let's move on and talk about the sampling methods. There are, in inferential statistics, many ways to perform samples. There's a simple random sample, which is where we select individuals such that each group or individuals has the same probability of being selected. Okay, we've talked about that. That is critical to having a successful experiment, right? You always use random sampling in order to ensure that your sample represents the larger population. But there are other techniques that can be used as well. In addition to random sampling, sometimes we might use strata, also known as stratified sampling. This is where we divide the population into groups and then take a proportionate number from each strata. For example, if we're doing polling for the presidential election, let's say, and we know that 60% of people that are going to show up to vote are Democrats, and let's say we know that the remaining 40% are Republicans, we may actually want to construct our sample to maintain the same ratios we see in the population. So if we sample 100 people, maybe we choose 60 that are Democrats and 40 that are Republicans to ensure that the proportions are replicated in the sample. Another sampling method is called cluster or area sampling. This is where I divide the population into groups and then randomly sample the groups. For example, let's say I want to survey students at SDSU on an upcoming ballot proposition, but it's unrealistic for me to get everybody's name at San Diego State. Maybe there's privacy concerns, so administration won't release that information. So I say to myself, well, I can't get everybody's name and do a simple random selection of people, but I do know that there are clusters of students on campus occupying certain rooms. So maybe I know there's 100 rooms on campus. I take the 100 rooms, and each room therefore becomes a cluster of students. And then I randomly select a room. If there's 100 rooms, I put 100 numbers in a hat, and I pull out one number, one room. And then I go and I ask those students about it. So I'm getting a random sample, but it's done kind of indirectly through these clusters that are more easily available to me than everybody's name on campus. Another sampling method is systematic. This is where I randomly select a starting point and take every nth data piece. Maybe I have a list of students at San Diego State. And what I do is I don't need to question all of them. So I'm going to take maybe every 50th name on the list of students. So I would take the first name and then the 50th and then the 100th and then the 150th. You see, I've created a system. Or maybe I select every other name, right? Or every 10th name. The system is randomly determining what my sample eventually looks like. Convenience sampling is non-random, and it's done just for efficiency. You know, maybe we're in a classroom and I poll the students to get a sense of what that class views are on certain topics. However, the problem with convenience sampling is because it's not random, we can't infer to the larger population. Whereas with these other methods, we can infer from the sample to the population. They have research value. One last thing on the methods. There is always a random element to these methods. For example, when you selected the 100 person sample, but you kept 60 of them Democrats and 40 Republicans, you're still randomly selecting the 60 Democrats from the pool of Democrats, and you're randomly selecting the 40 Republicans from the total pool of Republicans. Same thing with cluster area. Even though you're dividing the population into groups, you're randomly selecting from those groups you've created. I randomly selected the building that I chose to go and interview students in. And same thing, systematic. You're randomly selecting a starting point. Whether it's even numbers or every 50th number, whatever. It's a random selection, meaning that in all instances, other than convenience, we have random selection allowing for inferential analysis. Now let's practice using the bank's data set and Excel's random function. I want to show you how to actually create a sample. So let me pull up the data here. This is, let's say, population of banks that we're considering studying. And let's say we've got information on the bank's revenue, profits, and employees, but we can't study all of these banks. Let's say we want to go in and we want to do more research. Maybe we want to survey people that work in the banking industry, all of that, but we can't possibly look at all these banks. So we're going to select a random sample. Even though we have, it looks like, a total of 51 banks, let's select only 5. To do this, we're going to create a column in Excel called the random column, and we're going to put equals an Excel function random, and Excel will assign a random number to each of these cells. There we go. And then what we can do is we can sort our data based on the random number and just take the first, let's say, 5. So we're going to go to, let's go up here to data. We're going to go over here to sort, and we're going to sort by the random values. Okay, and when you click OK, watch what happens. Take a look at this. It's going to randomly create numbers, and it actually generates new numbers when you do the sort. So it's randomly created a selection of banks. So we would choose these 1, 2, 3, 4, 5. We choose these 5 banks to interview for our study, for our research project. Okay, that's how we use the random function. Okay, now let's talk about calculating the number of samples from a population. And I want to do this manually. So if we are selecting a certain n from a population n, and we're doing so with replacement, then this will be the formula to calculate the total number of samples that are possible from the population. For example, let's say that we have a population of 4 people, and we're going to select a sample, so this would be n, and we're going to select a sample of 2 from that 4. Well, how many samples can we get if we do our selection with replacement? That is, when we take one person out to form our sample, we put them back before selecting the second person. And the answer is 4 to the second, which is equal to 16. Okay, now what happens if we pull our sample from a population, but we do it without replacement? Then we need to use the combinations formula. And for this, we're going to assume, let's say, n is equal to 10. So we have a population of 10. Let's say little n, our sample is going to be 3. Plug in the numbers. Well, we first have our numerator, which is n factorial, so 10 factorial. Then we're going to divide that by 3 factorial times 10 minus 3 factorial. We can do the computations in Excel. And remember, Excel does have a factorial function. So put equals factorial and 10. That'll be our numerator. It looks like we have 3,628,800. So that's our numerator. 3,628,800. And then our denominator, we're going to have, again, factorial, but it's going to be 3, that's 6, and then 10 minus 3 is 7, so factorial for 7. Get this, and 6 times 5,040 is equal to 30,240. And so we can then take our numerator and divide it by our denominator, and we get 120. So there are 120 different samples that would be possible. All right, that's it. If there's any questions, please let me know.